Hey everybody, it's Jeff for CS161A. This week we're going to cover Chapter 8, which is Module 9. Chapter 8 is introducing functions. A little bit complex, and for those of you that haven't seen these before, there may be a little bit of practice before it starts to sink in. So we're gonna introduce the concept of functions and do a bunch of demos as usual here. If we go to Module 9 overview real quick, um, we'll talk about, why we want to do functions and what they do and so on. And you got, this is Chapter 8. Okay, so we'll get started here. As always, I do have PowerPoint this time, so we're gonna start with the PowerPoint here because I think it's a good way for me to set the context here. Often in these classes, we just like, here's like programming construct, here's what to do, here's how to use it, without necessarily connecting the dots on what the purpose of the construct is and why it's usable and why it's valuable. And the examples are so simple and contrived that often um, the construct doesn't seem necessarily to add a lot of value until you learn much later. So I'm gonna introduce the concept here in the context of couple real life applications that I've done over the last few years, which might help, right? And so I'm gonna start with a product that I've been working on here. Um, I wrote some production firmware from scratch in starting in 2020, over a year or so. These large capacity industrial air purifiers. It's not super complicated, so don't get me wrong, not super complicated. But there was a digital interface, and the user could do all sorts of stuff, right? The machine had to run, of course, and there was password control and automatic calculations and lifetime monitoring and other things like that. But there's a piece of the functionality that I want to kind of describe to help set the stage here. This firmware is, by the way, firmware, if you haven't heard the term, is just software that runs embedded on a custom custom computer circuitry or a microcontroller, right? So the software that's running on your smartwatch, for example, is technically firmware. And so it just means that, like on my watch, I can't like load and rerun and debug the code on my watch, right? So that's where the term firmware comes. Firm is, of course, firmer than soft, right? And so my firmware in this product here is about 6,700 lines of C++ code. By the time you're done with CS161B, if I were to show you that code, you would, be able to follow most of it, I think. I don't do a lot of super advanced stuff in there. And even by now, a lot of that code would look familiar. Okay, so in this example, this is a zoom up of the front panel or the top panel of the machine. You can see there's these three indicators here on the left. This is really all we're going to talk about for this machine. We got three indicators. Two of them are for standard features, right? Every machine has two of those indicators and one doesn't. So it's just the front panel looks different. That third indicator is for an option. Okay, so you buy the machine with or without the option. These indicators have some rules. If the machine is plugged in, if the machine's not plugged in, of course the indicators are off. If the machine is plugged in but not turned on, these indicators are off. If everything's good, right, if the machine is running as expected, the two standard indicators, which is the top one and the bottom one, are green, like shown here, but the middle one is off, and in this maybe is a nuance we don't need to discuss, but in the machine without the option, there's actually not even a cutout here, so you don't even know there's that third option, right? But the LED below is turned off anyway, right? Because you use the same circuit board is the point, right? And so they're green if the normal operation. And then if any of the indicators, any of the three features have a problem, that one or more indicators will be red. Okay, so for example, if a filter needs to be changed, or if there's a safety lock that's been disengaged, or the machine's been running for too long. I mean, I can give the list of these issues here. And so if you look at, like, if you were to look at that 6,700 lines of code, there's many places in the code where I have to check the status, right? One place where I check if a particular filter is nearing end of life and so on. I mentioned safety related already. Some are instantaneous in those cases. Others I'm checking only every 60 minutes because, if you're keeping track of how many days old something is, you really only need to check every 60 minutes or even less than that, right? And then I went and counted all the places where I checked one or more thing or I did one or more thing that caused those indicators to change. There's 15 places in the code. The code to actually turn on or off the green or the red is quite standard, right? It doesn't change, right? And so instead of having 15 different places where I turn green off and on and red off and on, I have a function. I have a group of code that I've separated, and that group of code will basically check some status flags. And if the flag says, hey, there's a problem, turn the red LED on and the green LED off for that feature. If all good, turn the green LED off and turn the red LED off. Even if the green LED is still on and the red is still off, you can do it again, right? And then otherwise, you turn off both when you're going into that standby mode or the machine's turning off and so on. And so without, spending a lot of time and showing you, quote unquote, the design document here, the idea here is that there's 15 places where I have to check something that might result in the change of these lights. And to make things simple, I have a function, and it's called drive indicators. That's the name of the function. It's about 100 lines of code because it's doing some other stuff, right? It's doing it. There's some indicators on the front of the machine as well that I'm not talking about. But I've written that function and I've pulled it out of main. It's a separate function. And then I can basically call that function. That's the terminology that said, hey, I want to run the code into that function. And the function will not just do stuff, but it could also return some status. And I'll talk about that as well. Okay, so that's your kind of high level description of what a function is. In the textbook, right, we also kind of describe what this is as a high level, and we jump right into some examples, right? So you could do that, of course, too, but I'm going to, of course, introduce, the concepts of functions as well. Okay, so all right, so we just went through the PowerPoint, right? And like I said, I started with this real life example to hopefully set some context here. What are some reasons you might use or create a function, right? One example is a function to input and error check a numeric input from the user. Okay, positive values only, no decimals, no other symbols, and so on. That's code that you might use over and over and over and over. And in fact, some of you have already experienced this, where in some of these programs where you're trying to get numeric inputs or currency inputs, the Ferry calculator and things like that, right? Where you might have the same error checking over and over and over. Another example might be a complex unit conversion that you need to do multiple times. And so you have basically mathematics where you've created a formula, and that formula might be as simple as the Pythagorean theorem or Fahrenheit to Celsius, or it might be way more complicated. And as soon as you have that formula in two different places, it becomes error prone, right? And many of you have gotten feedback from me on previous assignments that if I see duplicate code, it's a flag for me. And so far, it's because you have stuff that could be inside loops, right? And you have stuff outside loops, right? That's the main reason so far. But now you'll find that this is stuff that you can put inside a function, right? Another example would be a formatting/printing function to nicely print data, right? Tabular form, lining up things using some of the standard I/O features that we've discussed earlier in the class. And so the the book's examples are quite contrived. Actually, some of them are pretty good, but many of them are, here's two numbers, add them together and so on. So I just want to help connect the dots here on why these functions will be more valuable. And like any of these constructs, as you use them more and more, that will become more clear, right? Okay, so let's create a function. And I'll just finish my main here. And so I'm going to create a function, and I am going to, we're going to do this in a couple steps. Step one, a basic function. And I am going to go nuts with my naming, because it just helps with documenting what I'm saying and doing. In real life, I probably would not name a function that long, but maybe, I suppose, depends on the usage. Everything I'm doing in here should make sense, right? I'm going to set the variable max equal to a, but if b is greater than a, then I'll set the max equal to b. All right, you can do this a couple ways. You can say if a is greater than b, max is equal to a, else max is equal to b, or you can preset max to one of the two values and then override it if the other is true, right? And I probably will show you both ways here. A max of all right. Okay, so I have my name of my function here. I have nothing in between the parentheses, and we'll discuss what this means here in a moment. And we're also going to discuss what this means in a moment. Just hold off, right? So now if I run my program, let's see what happens. Nothing. I don't know why it took 8 seconds. That's nuts. It shouldn't have taken nearly that long. But the answer is nothing, because if you look, there's no lines of code here before this return statement, which I really also haven't talked about either, and we will here in a moment. Okay, so this code here does not get run until I call it. Okay, and so in order to call it, we need to we enter a statement, which is the name of the function. Okay, so now when I run the program, now this line 27, when it gets to line 27, it recognizes that as a function, and so it jumps up here and it will run this code. So I'll go ahead and enter my two numbers, and I get my answer. Okay. I can do it again, right? I can run it throughout my program. So there's my first call, and there's my second call, right? So there's step one, the basic function, and me demonstrating the value of not having to duplicate that code. Okay. It's really important to see here that it's not accessible, right? Watch what happens when I try to do this. Okay. I got lots of errors here, but yeah, it says, oh, sorry, max is a function name as well. So I'm going to change That's funny. I didn't catch that the first time I ran this. Max is a built-in function name as well. So let's just change that. Says MX is not a, it's unidentified. But wait a minute, I've declared it here. No, it's not accessible. It's declared only in the scope of this function. And we'll come back to this over and over and over because this is super important. Okay, so that's step one here. Okay, now let's, and by the way, I'm going to kind of overwrite stuff as I go. For most of the code, I've saved it, and you can kind of see I sometimes, my mouse is going off the screen and stuff. The file that I'll upload will have most of this, but you might have to reconstruct some of this. Okay, now what I'm going to do is add a return value. Actually, no, let's keep it separate because I want to compare them. So never mind. Let's keep that separate. Okay, step 2. Okay, I want to copy the function. Okay. And return the maximum. Okay, let's look at the difference of what I've done here. Okay, the first thing that I've done is I've changed what's before the function name from void to int. What void means is my function does not return something. It's void of a return. Okay? Sorry about the barking. In step 2, I'm saying that my value that I'm going to return is an int value. Okay? And so now, sorry, trying not to smile with those nonsense dogs here. What I'm going to demonstrate first. So now, if I, let's just do this. Int temp equals. Okay, this should work, I think. Okay, so I'm using my original function, get new 2 numbers and print the maximum, and I'm trying to get a return value from it to assign to the variable temp. And so now I'm getting a error here. You know, I must try to assign from an incompatible type void, right? Void is incompatible with everything, right? So that's your first test to show that you can't, a function that's void is not going to return a value. So now if I run it, this is the first time I run, and that's the second time I run. And so I send in my numbers, temp gets assigned to the value, and that's why I get the value 99 here. Okay, one thing to show you real quick, if I try, no, I did that already. I already showed you that. If I do this, this ran, but there's no destination for it. So temp never got overwritten here, right? I also could do this. I can just, except I don't need that anymore. Step 1, step 2. And I enter my number. This return value gets, basically this gets replaced by the return value. Okay. So far so good, it should be. Okay, now, A big limitation of this function in both of these cases is that the function has to ask for the information. And it is way more useful if my function is more versatile if I can give it the information, because information will be coming from different sources, right? So we're going to do a third version of this, which is takes two parameters, returns value. I should stick to using MX. Takes two parameters, returns values. Okay. Okay, so our name of our function is this. And so if I do this, do something like that, let's see what happens. I'm missing a brace somewhere. Extra brace. And I'm using my MX. That's funny, Max was working on the different computer there. Okay, so here we go. So in all three cases, I give it different values here, and I get my max value, which is these three different guys here. The value of this function, right? So now the function is super streamlined, right? And you can call it in different ways, right? I can input the variables and then call the function. I can call the function inside a loop as I'm doing different things and so on. And your code becomes much more versatile, if you will. Okay, so looking at my notes here, we can always pass any number of parameters, right? So I have two parameters. I can make this a max of 10 if I wanted, right? So you can pass 0 parameters, 1 or more. You always will return just 1, and that'll be of this type here, right? I can make this a char or a float or a double, and my function like a 2, if I made my own 2 upper, it would be a char, for example, right? But you can only return one thing. If you want a function that has to modify more stuff, then you just have to modify the variables that are declared up front. So I can do something like this, right? And I can say total equals total plus mat from MX. And then I can do this. And when I run this, you'll see my total is equal to the sum of my 3 maxes, right? So I set total equal to 0 up here. I'm accessing it inside here. And so in some ways I'm returning it, but I'm really not, right? I'm just accessing it. Okay? And so this is an important distinction. Sometimes people will write functions and just have no parameters and just modify the variables that are declared up here. Right? Variables declared up here are called global variables, meaning they're global means they can be used everywhere in your program. Okay, so let's jump back here. Functions are not just for pulling out duplicate code. I've kind of shown you that example and hopefully start to connect the dots from the air purifier example, but you can also use it to partition out a very complicated piece of code that just may be interfering with readability and maintenance. And you've probably seen this already in some of your assignments, where your flow is all kind of nice and then you have a bunch of stuff and it kind of just clogs up the code. And so now you're going to learn here that you can encapsulate that code inside a function and move it out. So for example here, let me turn this off because it's distracting. In a project that I'm doing right now, I'm writing some Internet of Things code where, so I have a microcontroller and it's connected to some sensors and things like that. And my main loop looks like this. While true, right? And true gets broken for a variety of reasons, but for the purpose of this conversation, don't worry about it. I set a flag, publish flag equal to false. I do some stuff, I do some other stuff, and I do some other stuff. The names are probably self-explanatory. I'm checking a bunch of sensors. I'm reading the GPS location of the device. I'm checking the battery level of the device. And if any one or more of these functions, if something's changed or something's flagged, it's going to create some data in this form of what's called a JSON. JSON is a text format that's used, I'd say mostly like in web applications and data going to and from the cloud. And originally from a language called JavaScript. But it's used across many languages now when communicating. So for example, if I have this IoT code and I want to send to some cloud software so that a dashboard or a phone app gets updated, I'm going to send this data in this format. Okay? And so check rack sensors is the only, so this code, if I were to show you, is, hundreds or 1,000 lines of code. This is the only place check rack sensors is called. But check rack sensors is 200, 300 lines of code. And so I don't want it inside this while loop because it obfuscates the flow, right? The flow is so clear here. I set my flag to false. I do some stuff. If my flag is true, then I do something else. Okay, read GPS is the same. It's got some nuances about how the GPS data is managed. If any of you have fiddled with GPS software, you might know what I mean. Reading the battery level is fairly simple, but it's also nutsy detail that nobody needs to see. So, and both of these might be used elsewhere or are used elsewhere. But the point is now my main loop is super slow or super small and super clear. So you'll want to use functions to group logical code, and then you can give it a very clear name like this. Okay, so let's keep going here. I want to walk through in the code. I think it is example. It's here it is. 862. It's the least common multiple calculator. I want to run through this example. And just going to use this as my kind of notepad to help with our notes here. The uploaded code will have this link, so you don't have to worry about this. Okay, so here's this example 8.6.2. The variable names in the textbook uses are obfuscated to me. I simplify that, and I'm kind of describing what's going on here. What this program does, and this is how long it is, it's 87 lines with all my comments. It does two things. It finds the least common multiple and the greatest common divisor of two integers. These are two functions that you may or may not know, depending on where you are in your math classes. Okay, if you don't know, it's okay. I think you still can kind of follow the logic here as we walk through it here. And you can replace the two functions. If you want to take this code and you don't want to do these, replace them with average or max or something like that. Okay, but I'm going to walk through just very, very briefly. I'm not going to explain the algorithm itself. Okay, first I have this function which I've called prompt for positive int. Okay, this is a function that doesn't take any parameters. It returns an int value. And basically, it's going to ask the user for a positive value. And if I enter 0 or less than 0, it tells me no, try again. So this is your error checking, right? And so I could use this, and I can put this code in a lot of different places if I'm asking for numbers without having to replicate this error checking. Okay, if I go down to main, let's see what we do here. We're going to enter the first value, we're going to enter the second value, and then I'm going to run my two functions to find the GCT and find the LCM. Okay, GCD, greatest common divisor, is the highest value that divides evenly into two numbers. Sorry, the highest value, right? So 5 goes into 25 and 100. Right? But 10 would not. 10 only divides into 100, but it doesn't divide into 25. Okay, with 140, 5 goes into both of them, 2 goes into both of them, 10 goes both into them, but the highest that goes into both of them is 20. Okay, so that's what the GCD does. This algorithm is called Euclid's algorithm, and I'm not going to explain it. If you look at it, it probably gives you a headache. There's this iterative thing where you're using the two numbers in tandem to find the value. I'm not going to explain it. Okay, and then the least common multiple is the value that can divide evenly, that the lowest value that both of those values divide evenly into. So 4 and 6, if you multiply those two together, 4 times 6 is 24. So 4 and 6, of course, go into 24. But 4 and 6 also happen to go in 12. Okay, so if you were to calculate this on your own, and I asked you to find the least common multiple of each of these, you would probably take 4, and you'd go 4, 8, 12, 16, 20, 24. You'd basically create a table of 4s, and then you do the same with 6. 6, 12, 18, 24, blah, blah, blah. And then you'd scan to find the leftmost number that matches. That's a time-consuming method, and that's how I've written the function in the past. But there's a clever way of using the greatest common denominator to find that. And so you multiply the numbers together and you divide it by the common denominator, and that will actually work here. Okay, so maybe more math. You didn't expect a math class here, but let's give that a shot here. If I enter 6 for my first, and if I do -5 or 0, it doesn't like that, right? 6 and 4, I get 12 as my greatest common denominator. Two even numbers, the least common multiple will always be 2. Always, right? And by the way, 1 doesn't count, because 1 divides into everything, but by definition, 1 doesn't count. Okay, so let's try another one. Okay, this one, in this case, I have to actually multiply the two numbers together. No, not quite. 330 times 10, right? So 330 these two numbers divide evenly into 3,300, and the least common multiple here is 10 in this case. What was the other example I had? 4 and 6, 25 and 5. Let's run that one real quick. So 25 and 5 is 5, the least common multiple. Okay, so this is this example here. So now when you can, if you're going through this, if it's confusing, you can jump back to this code and you can try it and play with it. One of very common function use is common use of functions is implementing a menu system user interface. Okay, so you're going to write a program that's going to say, you see this a lot, right? Add a song, add an artist, search by song, print the list, delete the song, whatever. You'll have a menu, and then you'll call functions based on each item on that menu here. I have another example here that I want to walk through. And I think I have that here as well. I'm gonna, if you give me a second here, I'm gonna copy this into a scratch pad, and I'm gonna construct it little by little, because otherwise I feel like it's too much to like jump right out of the batch here. Okay, so I'm gonna do two things. I'm gonna illustrate functions with this menu, but I'm also gonna illustrate a simple way to get your program running even before you've finished implementing everything. Okay, so let's start with, what is my program going to do? Well, thank you for not indenting. It's not helpful. All right, so I've written a program that is going to print on a menu, and I have five things that I'm going to implement. Well, kind of, because 4 is a TBD. Option 1, if you hit 1, we're going to play guess the number. Number 2, you're going to enter degrees in Fahrenheit. It'll convert to Celsius. Number 3 is we'll print the value of pi. 4 is a placeholder, and 5 is quit the program. So we're in this while loop, and we're going to say, while the option is not equal to 5, we are going to just run. So if I run this right now, let's see what happens. I print mine. Each time I enter a value that's not 5, including an invalid value, I'll just keep going through the loop. And once I hit 5, the program quits. Okay, so this is inside a while loop. Now what I can do is I can that was a fail with my copy and paste, wasn't it? I'm going to remove some stuff. Because we're gonna enter this one at a time. Let's do this. Okay. Also not yet implemented. By the time I'm done with this and you click on this link up here, hopefully it's back to normal, right? So, not yet implemented. Number 2, I have the prompt, but I don't do anything else, right? Number 3, not yet implemented. Don't know what to do here yet. Now I get my invalid option, try again, and I can quit my code. Okay. When you build programs like this, it's really good to do things in steps, because you saw some of the silly errors that I make, right? Mostly because I'm copying back and forth, but some of it is just stumbling. If you've typed in 200 lines of code and you have an error, it's harder to find and debug than if you only have 20 lines of code. Right? So you do want to do this stuff in buckets here. Okay, so now let's see. Guess the number. I've shown you that in the past, but I did not implement that in this. I did not implement that in here. So what we're going to do, if you look at this code, if option equals 1, I'm going to call guess the number. That's all I need to do. That looks good. Okay, but guess the number is not yet implemented. Once I implement it, I can put that code here. And it could be, do you want to play? Do you want to be the guesser? Or do you want the computer to guess? And you could do all that stuff that I showed you in that previous video. And in fact, you could find that code and stick that in here if you want to. Okay, so we're not going to implement that one right now. Let's do number 2, convert the degrees to Fahrenheit to Celsius. And that's going to return a floating point number. Could do float or double, right? I just did float here. So we're going to use our prompt, our function that I showed you, and then I inadvertently deleted. So let's stick that guy back in there. This is the function. Actually, no, this is a fancier function. Let's come back to that. There's my function. Showed you it in the other program. Prompt for positive int. And then we're going to say C is equal to F minus 32 divided by 9.0. Return C. So there's my formula, if I did that right. We'll have to test that. And here we will now notice in this version, I'm just calling the function here. I could put the prompt in here, right? And then I've kept the Fahrenheit value. And maybe let's do that actually. Let's run this. Got my programming languages mixed up there for a moment. Okay, 212 gives me 100 degrees, which is correct. Okay, so let's change this. Okay, we're going to say F degrees F equals degrees C. And we'll get rid of the prompt from there. Okay, see if that works. Okay, my problem here is, and this was something I was going to show you later, is I'm declaring int inside main, but I'm trying to access it here. So what I need to do is I need to pass it as a parameter instead. I could have moved the int f up here and had it as a global variable, and that would have been fine as well. Okay, 212 degrees F is 100 degrees C, 32F is 0 degrees C, and 85 is 30 degrees C approximately. Those are the 3 easy test cases for me to do in that case. Okay, so good, so that's working. Okay, so I've improved this a little bit by making my print statement, instead of just printing the answer and prompting in the function, I get my value first, and then I pass it as a parameter, and I print it here. All right. Option 4 I'm going to keep. I'm just going to leave that as is. And so now we're going to do option 3. And option 3, well, actually, there's one more thing I want to do. I am going to modify my prompt for positive input, and I'm going to also, if limit is greater than 0, That is a max value that is allowed. Okay, so I'm gonna add a parameter here called limit. And now this code I need to modify to flag an error if the number is 0 or less, or if it's greater than this limit. And if the limit is 0, you ignore the limit. Okay, so I have the code here. I'm just going to paste this in. Save a couple moments and let me explain what I'm doing here. So I have a while loop now. If the limit is greater than 0, then I'm going to add to my prompt here. I'm going to say enter a positive integer greater than 0 and less or equal to the limit. If the limit's 0, I ignore that. Okay, then I get my number. And then if my number is less than 0, I print an error message. If the limit is greater than 0 and my number is greater than the limit, then I print an error message. Otherwise, I'll break and return the number. Okay, so now what I could do is in my temperature, I can basically say max 400 degrees. So let's say for whatever reason I wanted to limit the temperature that could be entered here. Okay, so if I enter 300, I get a value. If I enter 400, I get a value. If I enter 405, it says nope, negative number, nope, 32 is fine. You can imagine modifying your input function to provide the ranges on both sides, because with a temperature conversion, you want to enter negative numbers as well. So you can, that would be the exercise to leave that with you, to change that enter a positive integer prompt to say, you know, where you can enter two numbers, and you got to, and if the minimum number is 0, then any negative number could be allowed, and you might need to add a third flag to allow the value 0, right, as a limit. So you can get fancy with these input validation functions if you want to make them very, very general purpose. All right, now the reason that why I wanted to add this limit here is because for the last piece of this menu-based program is printing pi, I haven't implemented yet. What we need to do is we're going to use a clever way to calculate pi, and I'm going to spend a few minutes describing this one as well. This one's kind of fun. And so, warning. Okay, so I've picked a constant here of about 2 billion, right? Let's do this just so that you see that, right? If you remember right, an int maxes out at a little bit over 2 billion if you use an assigned int, okay? I noticed with this code that this amount took a couple seconds. So if you start to increase your number of iterations, the program will be super slow. Okay, and I'll show you why you'll want to do that in a minute here. Okay, so we're going to, and I'm going to kind of describe this. There's a method called the Monte Carlo method, and some of you that have taken probability and stats will have heard of this. It's a method that uses random sampling to generate numerical outcomes. And so read that again. Use random numbers to generate a numerical answer. Doesn't seem like it would work, right? But it's a very valid method that's used in simulations and in some cases some mathematical calculations. It's a clever way to approximate pi. And I want to show you how to do this if you've never seen this before. And so we're going to create the function pi with iterations. Iteration. Ugh. pi with iterations. And we're going to give it a limit. And what we're gonna do is the variable names I'm using, I call them, I'm throwing darts at the wall, right? And the way I've described this, like on a whiteboard, is I draw a square, and I'm gonna start throwing darts at the wall. And based on where the darts land, and count the darts, I can approximate pi. Okay. Prompt for positive int limit. Okay, so I'm going to call this function. Let's look at how I might call the function, because I want to get that correct here. So down here, I am going to tell the user that they can enter the number of iterations up to that max value. And then it will call that function that I'm writing now with that, with that max as the limit, right? And so this max up here, which is 2 billion, is the highest number that you'll be allowed to enter, when we run this. So we're going to throw up to that many darts. Okay, then I am going to set my random number seed to some random value based on the current time. Don't remember if I've explained this before, but I know it's covered in the material. In C++, when you use the rand function and you run the program over and over and over, you'll always get the same first number and you'll always get the same sequence of random numbers, which might be okay. But if it's a user, if the user gets to interact and it's a game or something like that, then they can figure out that and they can exploit it, right? So instead, we're gonna initialize what's called a seed, and we're gonna use this time function, which takes the number of seconds that has elapsed since January 1st, 1970. That's what time does. And so every time you run the program, the seed will be different. Now you still can predict what it is, actually, if you're smart enough and you time things perfectly. But for this type of program, it's perfectly okay. Okay, we are going to initialize 3 double precision numbers. We're going to initialize our value, or we're going to declare 3 variables. I'll explain those in a second. We're going to initialize our value of pi, and we're going to keep track of the number of darts that are in the circle. And let me explain what that is, because this is the key, right? This is how. Actually, it's better if I draw it. I should just draw it. Let's do that. I should just draw it. Okay. We're going to take a square, and we are going to have our square be a 1 by 1 square. Using PowerPoint as a whiteboard is a little slow. Okay. And so this square has a square. This square has an area equal to 1, right? Because it's 1 by 1. Okay, now I'm going to take a... Oh, that did not work. That didn't do what I wanted. There we go. I'm close. I'm close. Why is that not working? Sorry. Let's make that. 6. There we go. Okay. This is a quarter circle. Okay. The quarter circle has area equal to, a full circle's area is equal to pi times the radius squared. The radius of this circle is 1. So let me write that as radius equal 1. So full circle area is equal to pi times r squared. R is 1, so 1 times 1 squared is 1. So the full circle area is pi. The quarter circle area is 1/4 of pi. Okay, hopefully that made sense. If not, pause and go back and look at it again. Okay. Okay, so this is my dartboard. So I put my 1x1 dartboard on the wall. I draw a circle on here. Okay, now I'm going to throw a dart. Okay, and so I throw a dart and it lands here. Okay, from here, I know the x coordinate and the y coordinate of my dart, right? So my x coordinate is about 0.6 maybe. My y coordinate is maybe 0.4, right? I can use the Pythagorean theorem. No, let me draw it the other way. I can use the Pythagorean theorem if I know this and I know this to calculate the distance, to calculate that. This line's distance is the same if I flip it, right? So in other words, if I know my x and y coordinate, I know the distance from the lower left corner to wherever the dart is thrown. If this distance is less than or equal to the radius, then it's in the quarter circle, right? So if this guy is silly thing. So if this guy is anywhere with a distance 1 or less, it's going to be inside the circle. If it's more than 1, it will be outside the circle. Okay, so I'm going to start throwing random darts at the wall. And I'm going to count at the end. I can count the number of darts in the circle and divide that by the total amount. And that gives me the ratio of the darts in the quarter circle. And if I multiply that by 4, it gives me the ratio of the darts in the circle to the darts outside the circle. And since I know those two areas, I can divide them to get an approximation of pi. I went through that super fast. Some of you are like, okay, I get that. I think I get that. Others is like, no, this is like, I haven't done this stuff yet. And that's totally fine. And so I'm not going to type out what I just said because we just talked about it, but I do have it in the notes. And so now let's start throwing darts. Okay, so to do that, I'm simply going to have a for loop. This is your nomenclature. To get a value between 0 and 1, you just run the rand function and you divide it by the maximum rand max. I think rand max might be 32,760 or 32,676, I think, or 678. And so if you divide by whatever that rand max is, if you divide by that number, you've basically shrunk your range to between 0 and 1. So I'm going to do that twice. And then I'm going to run my Pythagorean theorem, which is z squared equals x squared plus y squared. That's your Pythagorean theorem. And so I use the math function square root of x squared plus y squared. And then, like I showed you earlier, if it's less than or equal to 1, then the number of darts in the circle, I add 1 to that. So then, now that I've calculated, or I've counted my darts here, I go ahead and I do my division of the darts in circle and the darts total, and I'm casting it as double because otherwise it might do this integer. I didn't check. It might do the integer division here. And that's only a quarter of the circle. So to get the whole circle, I have to multiply times 4. And that should be all I need to do. And then I return my function. Okay, so now let's take a look at this one more time here. If I enter option 3, I'm going to tell the user, hey, you need to enter the number of darts, I should say, number of darts to throw up to that max iteration. And then I'm going to run the function, and the function actually asks for the number. So again, like we did with the temperature, how I moved it out, I can move it out here, but I'm just going to keep it there so that you see both different ways. Okay, let's see if it works. Option 3, I'm going to enter 100 darts, and I get a value 3. That seems convenient. I may have forgotten something. Let's make it 5,000. Oh, that's interesting. It happened the first time I ran it with 100. It actually evenly divided to 3. So I ran with 5,000 darts. I got 3.1472. That's not bad, actually. That's pretty close, isn't it? Let's run it with 5,000 again. 3.064. So you see, each time I run it, I am going to get different values because I'm throwing darts at the wall, right? Now let's make it 50,000. Keep doing that. 50,000, 3.135. 50,000, 3.14496. Numbers aren't terrible, right? Let's try 1 million. 1 million. 1 million. You guys are laughing at me here. 3.14298. 3.14118. Okay, how about 5 million? So I'm getting consistently my first 3, right? Or even 4, 3.141, 3.14 if you round up 1, 3.142, right? So I'm getting close, right? Let's do it a couple more. Now let's do our max here, 2 billion. Now when I enter this, let's see, 2, 3, 4, 5. Oh, no, I entered, sorry. Let's try that again. Okay, let's do, sorry, I got confused there. 3, 2 billion, 1, okay, 3.1415. I was running this earlier, and it was taking like 2 seconds every time I ran my number. So it's actually giving me some more compute time here on Replit right now. Maybe I'm off the peak time or something. But I noticed that as your number gets bigger, your for loop will just take longer to run, right? And if you want to make this more accurate, instead of running 2 billion iterations, you probably want to run 10 billion iterations, right? And, but clever method, right? I got way off track here to show you this. Clever method here to um, approximate pi using random numbers. And it's kind of fun here. And so it shows you here that I can make this program more and more and more complex. And you keep it out of this core code here so that your menu is nice and clean. That's the message here that I'm trying to show in this example, obviously. Okay. All right. I think that's everything I wanted to show in the menu program. All right. Okay, I want to okay, we've shown that already. Before we wrap up, I want to talk about the scoping one more time, but let's review. There's two things I want to do, right? This is not in the uploaded code. I've showed most of these as we've walked through them. Okay? Rule number one, a variable declared inside a function cannot be accessed outside the function. Okay, so if you have int x inside the function and you try to see out x in main, it's not going to work. Okay. The same variable name declared inside two functions are essentially different variables and do not interfere with each other. So I do want to demonstrate that. All right. Okay, so here's some other code. There I have all these replets going. Okay, so I have a function here. It's kind of silly. I just take an input value 200, I add it to 10, and return that value. Okay. Okay, rule number one. I can't access this variable. Okay. This variable is internal to the function. When I run the function, it's created, it's used, and then it's discarded. The next time it's running, same thing, right? It's in fact a new version of the same variable. Okay. Rule number two. Back to the PowerPoint. The same variable name declared inside two functions are different variables and they do not interfere with each other. So this A and this A are different. They basically, neither of them exist at the same time because I'm either running in here or I'm running in here. Okay. Okay, rule number three, a variable declared as a global variable can be accessed and modified by function, but per rule one, not vice versa. So now I can do this. Let me show you this one. So if I run this now, A is equal to 10. So I return 200 plus 10. I take A and I multiply it by 2, so A now becomes 20. So then when I do my 200 plus 20 now, and I get 220. Okay. There's actually a rule that I missed, I think. What if I have this? What if I have A up here and A down here? Let's see what happens. If you look, I got the same value. even though I modified A. So let's see what's going on here. Okay, I'm going to print A out before and after every statement, basically. Let's see what happens. A is equal to 10. Then I run my cout, and I use 99 as A, right? A is equal to 99 in here. In fact, let's do this. Cout inside function, A is inside functions, A is 99, but then A is back here as 10, and then it turns into 20. But again, when I go into the function here a second time, 99 is used. Okay, so again, and I don't have this in the rules, do I? It's really, we're able to, okay, so this is, no, it is. It's rule 4. A variable declared as a global variable, but also inside a function has the result to that for loop example that I showed before, which is what I just demonstrated now. So, in other words, they don't collide. And so this could be good or it could be bad. And if you make the mistake of thinking the variable is going to be updated, but it's not, or vice versa, you can get into trouble. Okay, and then finally, rule 5, when a function is called the second time, it does not remember any state from variables from the first time. In other words, as soon as the function returns, it discards all variables, values. So again, if we look at, again, this code, this value of A is created and used only inside, and then it's gone. Okay, so these are some distinctions that as you practice will become more and more clear. And if you go 6 months without hitting a bug because of this, I'd be surprised, frankly, because every now and then, I see it. I see it with developers. I do something like it myself where I rename a variable and I forget that I already have that variable name somewhere else, and they clobber each other. And some software tools can be smart enough to give you they do some checks, some guideline checks to say, hey, you're duplicating things. Naming conventions help as well. So and different development environments may or may not help here. Okay. So some rules here around remembering how these variables work. Again, this is around scope. And I mentioned this for loop that I showed before. I want to check in my notes to see, yep, I do have that. So let me refresh on what that is. Should have showed it to you first, right? I showed you this 1 or 2 modules ago, right? I set I equal to 10, but then I used int I here. And I went from 0, 1, 2, 3. And then once I exited the loop, I became 10 again. Same thing, right? The functions work exactly the same. This is called local scope. Variables up here are called global variables. They're used everywhere. Variables declared here are local to the main function. And then a variable used here is local to the for loop. All right, back to the PowerPoint. I think the last thing I want to recap here. Some 4 questions to think about here. Does moving code into functions make your code more readable? Question number 2, does it make your code more maintainable? Question number 3, does it reduce the memory size of your program? And question number 4, does it improve the performance of your program? So question number 1, yes, almost always yes. I could, of course, contrive an example where it doesn't. But if you think back to the menu programs I've illustrated or some of the other things, the prompts, prompt error checking, and so on, it is almost always going to be yes. Okay, so question number 2, if it's more readable, follows number 1, right? Of course, if your code is more readable, it's going to be more maintainable. Okay, how about memory size? Okay, so this is an interesting question, right? If you look at the file size of the program, right? So if we go back to my GCD LCD example, okay? So this is the code for doing the greatest common denominator and least common multiple. Let's look at what I'm doing here. I am calling the prompt for positive int twice. And so this code here, which is, if I were to remove the function and I were to take these 1, 2, 3, 4, 5, 6, 7, 8 lines, I'd have to basically put them here and here. So I'd add 8 lines twice down there versus 12 lines here. This code and this code would be pasted below, but if you look at the least common multiple, it calls the GCD. But if I put the GCD code down here and I kept its value, then I wouldn't have to call it again, right? So in terms of the lines of code, maybe it's a wash. It's going to be a little bit less, I think. But that's not the question I'm asking. I'm asking if it reduces the memory size. Okay? And the answer at first glance, if I look at this, is, well, yeah, I probably will, because I have less code. However, the functions have overhead, which is, we're not going to talk about it much here. We'll talk about just for a couple minutes here. Functions have overhead. And so the answer here is it depends, but generally not. And you're going to give up some space for the modularity and readability. And then your next question around the performance, will my code run slower with function calls? And the answer here is it depends, but yes, generally, but no, generally not. Okay. And so, and there's some reasoning for this. It's the same. I have a little bit more here. And so, if you continue on in computer science, whether it's here or OSU or somewhere else, and you start to learn about the operating system and how compilers work and things like that, you're going to learn about a concept called the stack and how function calls are handled inside compiled programs. Functions do add more overhead. They often slow down runtime, but in almost all cases is the right trade-off. It's outside the scope of this class, but I bring it up because the book does mention it. And I'm going to just show you where that is briefly. And so in this complicated diagram, it's effectively describing what I'm talking about here. So this is an exercise for you if you're interested. Kind of describes what might happen here. Short answer is that you're gonna 99% of the time you are trading off readability and maintainability and less bugs, most importantly functionality, right? And with potentially performance. And unless you're on embedded devices where memory and performance is very, very fine-tuned with hardware, this has become less and less of an issue over the last 20 years, for example. So, all right, check my notes one more time. I think I covered everything I want to cover. Let me know what you think about how I added the industry programs as examples, if that was helpful or not. If not, I'll take it out for next time. If it is, I can add more of it. I'll be interested to hear on that. And happy coding here with functions, and we'll talk soon.